So we're going to learn how to find the volume of a solid. So when you want to find the volume of a solid, there are three major methods, what we call the slicing method. Slicing methods turn it to a disk method in a special situation when you have circular regions, circular cross sections. But this slicing method is a general technique, and we're going to discuss the disk method in a different section. And then after that we have the washer method and the cylinders method or the shell method, so we can discuss them separately. So let's talk about the slicing method. So let's say you have an object like this. So what we're gonna do, we're gonna place the object in the coordinate system. So you're gonna bring a coordinate system and place it here. So this is the other part of the object. So what we do, we place the coordinate system here. So this is the coordinate system. um, So I'm gonna go a little further down. So we place the coordinate system here. So the argument is how you do it. We place the coordinate system so that it is easy to find the cross section area. So we have the object. We place the coordinate system, and now what we're gonna do, we're gonna pick a point, and so we're gonna pick like a random point x in the interval. So let's say this is gonna go between a value and the b value. So those are the x limits of the object. So what we can do, we're gonna make a cross section. So we're gonna slice it at that x point. So let's say once you slice it, this is what you get. So it's like that. So there's a slicing goes like that, and on the other side that you cannot see, so it can be like this, and the okay. So that's a slice. So you can make it more visible like that. So that's the slice you have. So you can see that this is not really a, I mean it's a disc, but it's not a circular disc. So because it's a disc, when you cut it, it's thick. So that's a disc. So what we're gonna do, so this disc has a thickness. So this thickness, what we normally call the delta x. So this is delta x, or in limit you can call it dx. So it's up to you how you write it. Some people write it delta x, some people write it dx. Delta x you write when you talk about the Riemann sum. We write delta x when you talk about the integral. So it can be dx or delta x. So it's up to you how you write it, but remember they have two different meaning. Okay, now what we're gonna do is we're gonna find the area of this region. So let's say you can find this area somehow. Okay, so when we talk about different problems, it will be clear what we mean by that. So we're gonna find the area of this region. So I'm gonna call it ax because a function of x, because it's gonna change. So that's the area of this region, base area of this disk. Okay, it's not a circular disk, it's just a disk. So ax is the cross section area. So cross section area, and then what we can do, so you can, once you look at this one, you can see this is like a cylinder. So this is how it looks like. So you have that, and then it's gonna go like that. On the other side, some shape. So it's gonna look like that. So that's the area we are talking about, and that's the thickness, delta x or dx, depending on how you want to interpret it. Okay, so yeah, so that's the disk. Now what we can do is we can find this volume of this cylinder. So this is like a cylinder with a base area x. So we know that, so we can say this is the volume element. So volume element is ax times dx. So that means if you want to find the total volume, so it's simple. Total volume is the integral. So what we're gonna do, we're gonna find just one small area, one small volume. So one small volume is the base area times the height. So that's the area. So this is the area of the base, and this is the height. Okay, that's the height. Dx is the small thickness. That's the height. So that means what you're gonna do is you're simply gonna add them. Add means you can integrate them. from between two values, whatever you have, A to B. So that's the formula for the volume under the slicing method. So AX is whatever the cross-section area. So that's typically how you do a problem like that. So what we're gonna do is we're gonna look at several different cases. That's the base area, and we assume that the top and the bottom have similar area. They might be slightly different depending on the object, but we assume that they are close together because dx is really small. Okay, good. So how to do a problem? So these are the kind of steps to do a problem of this type. So the first one would be for these kind of problems, it's always a good idea to sketch the solid and the typical cross sections. Okay, so sketch uh, the solid, sketch the solid and a typical cross section. Sketch the solid and a typical cross section. Typical cross section. Good. And then the part two is we're gonna find a formula for x. So find a formula for x. Find a formula. Find a formula for the area X. Okay. Um, or a Y, because sometimes what happen, it is easy to do it the other way because you can cross perpendicular to the x-axis or you can cross perpendicular to the y-axis. So sometimes there are some objects those are easy to take the cross section perpendicular to the y-axis. So so it depends on the situation. So it's a x or a y. And then the third one is we're going to find the limits of integration. Find the limits of integration. Find the limits of integration. And number 4 is what we're going to do is integrate x or ay. Okay, integrate x to find the volume. To find the volume. So those are the kind of typical steps for this. Uh, so I'm going to write a note. So sometimes what happen, we try to find the x, but it is a function of, sometimes it's a function of y. So you cannot do that. So so what you need to do that, so you can say rewrite, is a major step, rewrite x in terms of x before integrate. Okay, before integrating, because you cannot have two different variables, so you just should have one variable. So it's a dx problem, you have to express ax in terms of x. If it's a dy problem, you have to express ay a in terms of y. So that's the kind of difference between the two. Okay, so let's try to solve a few problems. So now again the question is how to find, how to decide whether you you slice perpendicular to the x-axis or you slice perpendicular to the y-axis. So it depends on which is easy to find. Okay, whether it is easy to find ax or whether it is easy to find ay. That's how you decide whether you're gonna cut perpendicular to the x-axis, you're gonna cut perpendicular to the y-axis. Okay, let's do the problem now. So the problem says a solid is placed between two curves y equal x squared and y equal 2 minus x squared. So those are two parabolas, one concave up, one concave down. The cross section perpendicular to the x-axis are squares. So that's the important part. So if you look at the cross section perpendicular to the x-axis, so that means if you slice it perpendicular to the x-axis, you see the cross section looks like a square. Okay, that's a major information. So cross sections are like squares. So what we're gonna do, so let's graph the situation. Let's first graph the two curves, and you can see that the one is y equal x squared, the other one is y equal 2 minus x squared. That one gonna be 0 at plus or minus square root 2. So then the graph looks like um, so, and then you can see that this is square root 2, and this is negative square root 2, and then this is y equal x squared, and this is y equal 2 minus x squared, the upside down parabola. So what you need is, we need these integration limits that we can find setting the two curves equal each other. But let's look at the other one. So what they say that once you slide it perpendicular to the x-axis, that's x-axis. So if you slice it perpendicular to the x-axis, so your typical cross section looks like that. So that's the small cross section. So the gap is dx, is in the x direction. And so what they say that when you cut it, it looks like a square. So that means now what you get is, you get like a slab uh, with a square base. So that means it looks like this. So we can draw it like that. Uh, so we have that, and then so there's a thickness. So we can add some thickness like that. So that's how it looks like. And then also inside looks like that. Yeah, that's what it looks like. And then the length of the base. So you can see this is B. We call B the base length, and that base is exactly this sitting here. So that's that base, and it's coming out or going down. So so that's the part coming out, B. Okay, so that's what it looks like. And this same base that we uh, color, so that's that base down there. Okay, good. So that's what it looks like. Now what we want to do is, we want to find the actually I'm gonna mark this B on the other side, because so that's the B. The height and the width are the same. Now what we want to do is to find this area, the base area in this case. So what's this area? So this area is, you can see this is a square. That means it is base squared. Now what is this B length? So you can see the B is simply the top y value minus the bottom y value. The top y value is 2 minus x squared, minus the bottom y value is x squared. So that's the B, but you have to square that. So that means, in other words, this is 2 minus, um, so it is 2 minus 2x squared squared. So that is the formula for the base. Now what we're going to do is, we need to find the limit of integration, and then we can integrate this one. So for intersection points, what we can do, we can set them equal. So we can set x squared equal 2 minus x squared. It doesn't matter which one comes first. So this is 2x squared equal 2. In other words, you can see x squared equal 1, so x equal plus or minus 1. So that means those are the limits. So this is minus 1, this is 1. So that's the limit of integration, going from -1 to 1. Now we can write the volume, because we have everything we need. So the volume is simply a to b ax dx as a formula. So but we know the limits are -1 to 1, and the ax is, it is 2 minus 2x squared, that's b squared dx. And the question is, so we done, we have everything we need. Now it is just the algebra part. We're gonna integrate this. So to integrate that, what we can do first is, we can expand. When you expand, you get 4, and then we multiply the 2 and multiply by 2. So it is 8 x squared, and then you can square the last one, which is 4x to the fourth power. When you square, you get 4x squared, and then dx. So this is a very simple integral. So this is how we can do it. So you're gonna get 4x and then minus 8 third x cube plus 4 fifth x to the fifth power, and you're going to integrate between 1 and -1, and you can see that this is a odd integral, so that means you can write this as twice of uh, one side. So somehow you will only need to plug in the value and simplify. Once you plug in the values and simplify, you should end up getting 64 over 15 whatever the unit, a cube. So unit cube, so that is the answer for the problem. Okay, so let's do another problem. So now what we can do, so what if so we can say what if the cross sections are the cross sections, what if the cross sections are equilateral triangles, equilateral triangles. So that means we need some other formulas from trigonometry. So let's do this problem. So the problem says the base of a solid is the region between the curve y equal to square root x and the interval from 0 to pi on the x-axis. The cross section perpendicular to the x-axis are equilateral triangles. Those are equilateral triangles right now. Last time it was a square, but now it's equilateral triangles. So the question is find the volume of the solid. So let's graph the situation. So we have the interval on the x-axis like that. That's the x-axis, and this is the y-axis. So this is the 2 square root sine x curve. So it looks like sine, but it's square root. So it's gonna go like that. Now what it says that the cross sections are equilateral triangles. So that means if you pick a typical x, so if you cut perpendicular to the x-axis, what happened now is they are rectangles. Not they are rectangles. They are equilateral triangles. So that means it looks like a triangle like that. So that's the situation. Um, So, so what we have here, so we have the x distance, that's the x coordinate, and the y coordinate, that's the y coordinate. So the cross sections are equilateral triangles. So these are like triangles. If you cut it, you get a solid triangle like that. So this is a solid triangle. If you cut it, it looks like a triangle. So what you want to do, and this is the curve y equal to square root sine x. So what you need now is we need to find the we need a formula for the base area. So in this case, y is the height, so we need to find the base area formula. So so let's do that. So what we can do, we can look at the simple triangle, equilateral triangle. So this equilateral triangle. So let's kind of derive a formula that you can use in the future as well. Let's say the base length is b. So it's a b. That means all of them are b. This length is b. And then what we can do is we need to find this h, the height. So we know that this one of is half b. This is also half b. So we can use the Pythagorean identity to find h. So we know that the h squared plus b over 2 squared equal b squared from one of those triangles. So that means h squared is, you get b squared. Yeah, I'm gonna add one more step here. B squared over 4 equal b squared. So that means you can get h squared is 3 uh, b squared of 4, so that means h is a function to the square root. You can see that square root 3 over 2 b. So that's one way to get it, and also you can use trigonometry, because we know this angle is 60 degree. So from that you can write a tangent, then from that also you can get that. So somehow h is square root 3 of b. Now we can write the formula. So the area of a triangle formula. So that means area of the triangle is simply half base times height. So it is half base is b, height is square root 3 over 2b. So if you simplify, you're going to get square root 3 over 4b squared. So you can use this as a formula. So if you know the base length, the area of equilateral triangle is square root 3 over 4b squared. Okay, so you can use this as a formula. So that's exactly what we need. So that if you know the base length, the area of the triangle is square root 3 over 4b squared. So we can use that now. So but in our problem, what is the base length? Base length is simply the y coordinate. Okay, base length is y coordinate. And then also, what are the limit? It's going from 0 to pi, because we know that at pi, sine pi is 0, that's why it's 0. Good. Now we can write the volume for this one. So the volume is um, it is again a to b uh, ax dx, a to b ax dx. So let's plug in the values. So it is 0 to pi, uh, and then we can find the a. So what is a? So it is square root 3 over 4 from the formula we derived, and whatever the length, so it is y is the base length, so it's a y squared dx. Okay, now the issue is you're going to integrate this with respect to x, but your function is y, so that means we're going to replace that. So once you replace it, so you're going to get the integral going from 0 to pi square root 3 over 4. We're going to replace y. Y is simply, we know that is 2 sine x square root. It's too close. So we can write this one as 2 sine x square root, whole thing squared. Okay, that's given. Okay, that's given, because y equal to square root x. Okay, now we can simplify this, and if you simplify, you can see 2 squared and 4 get cancelled, so you simply get square root 3 0 to pi sine x dx. This is a very simple integral, so it is square root 3 sine means negative cosine. So this is negative cosine, the values are pi and 0. So so let's plug in. So negative cosine pi minus will become plus cosine 0. We know that the cosine pi is a cosine. So cosine pi is negative 1. Cosine 0 is 0. Cosine 0 is 1. So this is 1. So and then what happen is you're gonna get negative positive 1 1 2. So you get the final answer as 2 square root 3. And this is again unit, it's a volume unit cube. Yeah, so we have square root 3 1 minus, nope, we have what we have here minus 1 plus 1. Okay, that's it. Okay, so that's the volume of the solid. So let's do one more problem with a different cross section area. So how about this? So this problem has two parts. So the first one is so what it says that a solid lies between the curves y equal 2 minus 3x squared and the x-axis. So the one is the upside down parabola and the x-axis. So there's a solid between the two. The cross sections, so that's the important part, the cross sections are perpendicular to the x-axis, to the y-axis. Actually, now this turn on the x-axis, the y-axis, perpendicular to the y-axis are circles. So they are circles. So find the volume. So it's a very similar problem. Um, so let's graph the situation. So we have the curve. So it's a parabola, upside down parabola. Um, yeah, so it didn't come good. So it's upside down parabola. Good. Uh, and then what are these numbers? And you can see when you set it equal to 0, so you can see that the two numbers are, so it is, we can do 2 minus 2/3 square root. So we have 2/3 square root negative, 2/3 square root positive. So those are two numbers goes here. Now what it says that if you cross it perpendicular to the y-axis, okay, they say that if you cross it perpendicular to the y-axis, so let's cross it perpendicular to the y-axis, uh, like that. So if you cross it perpendicular to the y-axis, so what happened? The cross section is a circle. So the cross sections are circles like that. So what you want to do is we want to find the we will find the area of that typical circle. So but we know that this is the x coordinate. And see, this is simply that because if you pick a point here, xy point, okay, if you pick xy point, this is simply the x coordinate. So the radius is simply the value of the x coordinate. And then you know that we're going to move this along the y direction. So this is dy, the thickness is dy. So what you need to do is to find the radius. Okay, after you find the radius, then we can find the area. So what we have is we know that y equal uh, 2 minus 3x squared. This can give you x is so you can write this as you can say y minus 2 1/3. So we can write this one as y minus 2x squared, because since we need x squared, I'm going to leave it like that. I'm not going to go for x. So that's the x value. Now we can write the formula for the area. So the area of the cross section. Remember, like here, what happened when you cut it? When you cut it perpendicular to the y-axis, they are circles. Okay. So the area of the cross section. So the area of the cross section. Area of the cross section. So now we write as a y because we can integrate with respect to y. So it is pi, the radius is x, so it's pi x squared. But we already know what is x squared, so we can plug in. So it is pi 1/3 y minus 2. So everything looks great because it's a function of y now. So that means we can find write the volume formula. So the volume is simply the limits are c to d. We write that when we write it using y coordinate. So 0 to, so and then ay dy, ay dy. So what are the limit? What is the bottom limit? You can see the bottom limit is 0. What's the top limit? And you can see that when x equals 0, it's going to go up to 2. So the top limit is 2. And then ay, we have a formula, so we're going to plug in here. So it is pi third y minus 2 dy. So this is a very simple integral, so it's a pi third. If you integrate, you get y squared over 2 minus 2y. You can integrate between 2 and 0. When you plug in 0, is gone. When you plug in 2, you get what do you get? So uh, I think there's a typo, so this is has to be 2 minus y and also 2 minus y. This is also 2 minus y. That means this can change the order. So this is 2 minus y, 2 minus y, 2 minus y. So that means this is 2y minus y squared over 2. And then once you plug in the values, you're gonna get pi over 3. You plug in 2, this is 4 minus 2 minus 0. So that means you get 2 pi over 3. This is a volume, so unit cube. So that's the answer for the problem. Now what we can do as part 2, you're going to try this problem if the cross-section areas are let's say squares. Same problem but with the cross-section area as squares. So redo the problem if redo the problem if the cross-section area if the cross-sections are squares. Okay? So that's the problem. So you can try that problem. So let's use the technique to do a special problem. So the question is how to find the volume of a pyramid. So let's say we have a pyramid with a base length b and the height h. So you drop a perpendicular to the base and that's the height. So the height h. So the question is how to do a problem like that. So you have pyramid which has the base length b and the height h. So what we're gonna do is we're gonna place it so that um, the vertex, that's a vertex, is at the origin. So that's how we do it. So we're gonna place the origin. So then the base goes like that. That's the base. And that's the x-axis. So we're gonna put the x-axis here, going like that. So now what we're gonna do is, so we're gonna so that's the pyramid. So it's gonna go like that, go like this, go like that, and yeah, it's not straight. So it has to go like this. Okay, so that means the other side goes like that. Because this side you cannot see, so that's why we draw it using a dotted line. Good. So that's the pyramid. Now what we're gonna do? We're gonna cross this at the x point. So let's cross it. So we're gonna pick a x point somewhere, and we're gonna look at the cross section area. So this is how it looks like. Okay. So it's gonna go with these two and that, and go down, and go there. Okay. So that's the typical cross section at the x position. So that's how it looks like. Good. So the goal is to find, so that's the x. So it's x distance away from here, from the origin. That's x distance. Okay. So the goal is to find the base length. So if let's say this is b, that's what we assume. So this b. So what we can do, we can look at the cross section. So if you look at the cross section, so let's say um, the length of one side is maybe like r. So let's say one side is r. So that's the length of one side of a typical cross section. So that means you can draw it like that. So that's the base B. So that's the typical cross section. That's the x-axis. So we can draw it like that. So that's the B, so 90 degree. So this is B, and this is R. That's what we're looking for, and that's the x distance from here. And this is h because we know the height is h. So now what we can use the similar triangles here. So by similar triangles, we're gonna get you can say r over x is equals to b over h, because that's what corresponds to b over h. So this is gonna say that r equal b over h times x. So that's the relation we need between r and x. Now we can find the area using this one, because that's the base length. This is square. Okay, so this is square. Uh, so that's the square. So let's use that. So that means the area for cross section. So area of cross section, this which is square, so we say ax, which is the r squared. We take r as the length, so that means r is b over h x squared. So in other words, b squared over h squared x squared. Okay, so that means the volume is volume of the pyramid. Volume of the uh, pyramid, which is okay. What are the limit? It's going to start with 0. It's going all the way to the height. That means h. You can see you can go up to h. Ax dx. So we're going to plug in here. So it is 0 to h b squared h squared x squared dx. This is a very simple integral. So this is b squared h squared. This is x cube uh, over 3. That's where the 3 coming from. H to 0. When you plug in 0 is gone. And when you plug in h, so it simplifies very well. And you can see that you get 1/3 b squared h. 1/3 b squared h as the formula. So that means the volume is 1/3 is 1/3 b squared h. So you can remember this as a formula for the volume of a pyramid. Next, we're going to talk about what we call the disk method with circular disk. So as an interesting problem, you can do this one. So you can say find the volume of a cone with base radius r and the height h. So that means you have a cone which has a base radius r and the height h. So that's the height. So which is h. The radius is r. And so you can show that this is exactly equal to 1/3 pi r squared h. So see whether you can get this answer using calculus. Okay, so